Hello student, welcome to our lesson today. We are going to continue with the nuclear equations, but in here we are going to discuss radioactive decay series. Now, when a radioactive nuclide decays, a new nuclide is formed, and if this new nuclide formed is radioactive, another decay will occur, and if other products are also radioactive, the process will continue. So this will continue until a stable nuclide is formed, and the process constitutes a radioactive decay series for a particular radioactive nuclide. For example, you can have a radioactive decay of thorium or uranium. In other words, when we talk of radioactive decay series of thorium, it means that thorium, which is radioactive, will continue decaying until you get a final product which will be stable. So radioactive decay series represent the sequential and continuous disintegration of unstable nuclide until a stable nuclide is formed. For instance, we have thorium-232 that is represented by the following decay series. We have thorium-232, it undergoes alpha decay to become radium-228. Then, if you look at the mass number is reducing by 4 and the atomic number is reducing by 2. Then this one that is formed is also radioactive. It undergoes beta decay. When we talk of beta decay, we have an addition of 1 in the atomic number. So it becomes actinium-228, 89. Then undergoes another beta decay to become thorium-228, 90. Note that this thorium and this thorium are isotopes. So we just check the atomic number. Remember, isotopes have different mass number, but the atomic number is the same. So this is thorium-228, this is thorium-232. So for you to know the element that is formed after a particular decay, you just need to check the atomic number. Remember this atomic number. After checking, you can be able to know which element is formed. Then, after this thorium-228 emits an alpha particle to become radium-224. Note that this is 224, 228 minus 4, you get 224. Then 90 minus 2, you get 88. This is radium. Then this one is also radioactive. So it undergoes alpha decay to become radon-220. And this is the atomic number, which is 86. I want you to note that whenever we have alpha particle that is being emitted, there is a decrease in mass number by 4, and there is a decrease in atomic number by 2. So you can be able to know the next element or the next nuclide. So this one, radon, again undergoes alpha decay to become polonium-216, 84. This one is also unstable. It releases an alpha particle to become lead-212. You can be able to see that the mass number has reduced by 4 and the atomic number have reduced by 2. So we have 82. Then we have beta particle being released here. So we have bismuth, which is 212. The atomic number has increased by 1 to become 83. And this one becomes now thorium, which is 208, 81. So you can see that this is alpha particle. So this one has reduced by 4, and this one has reduced by 2. That is from 83 to 81. Then finally we have a beta particle that is being emitted here to give us lead-208, 82. So this lead and this lead, if you look at the atomic number, it's the same, but the mass number is different. So these ones are what we call the isotopes. Note that this lead-208 is stable, but this one is unstable. So this one represents what we call thorium decay series. And this decay is natural decay, and it ends when we have a stable nuclide. And in our example here, our stable nuclide is lead-208. If you look at that lead-208, you'll find that the neutron-proton ratio is about 1:5:1, which again lies within the stable region. This one, we call it now thorium decay series. Then from there, we can move to nuclear fission. Now this one is a process in which a nucleus splits into two or more lighter nuclei when bombarded by a fast moving neutron. So fission is splitting. You have a nuclide, then you bombard it with a neutron that is moving with a very high velocity, then that nuclei or that nuclide splits by two. This generates a lot of or a large amount of energy, and there is also emission of neutron. Now, it was discovered that if you have uranium nuclei or nucleus and it is bombarded by a neutron, then the uranium nucleus splits into two almost equal nuclei as shown in this diagram, as shown in this equation. We have uranium-235. It is bombarded by our neutron here to become barium, and this barium also is radioactive. It releases krypton, and in the process we have the emission of neutron, and this neutron, they are three because we have to balance our equation, and in the process there is liberation of energy. Now the uranium-236 splits further to form barium-144 and krypton-90. The mass of these products, when added, these are the products, must be equal to the original mass of the nucleate. For instance, if you look at the atomic number here, it is 56 plus 36, you get 92. Then you have 141 plus 92 plus 3, you get 235. So your equation is balanced. This one is now an equation that is representing nuclear fusion, the splitting. These are the products. Then from there, the three neutrons produced further can bombard other nuclei, and more electrons or more neutrons will be formed. And those neutrons that are formed due to the process of this nuclear fission, then we call them fission neutrons. And the process, because it is continuous, we call it chain reaction. In that process, the energy is liberated, and this energy is liberated due to the fact that the total mass of the product is slightly less than the mass of the initial nuclide. Therefore, this difference is radiated as energy. Protons and neutrons that we call nucleons are kept in that small volume of nuclei by what we call the binding energy. Remember, the protons and the neutrons are found inside the nucleus. But how are they maintained in that small volume? We have the binding energy. So in the process of splitting the nucleus, that binding energy has to be released. And this is what we are having here. And when it is released, we call it now nuclear energy. So the binding energy is keeping the protons and neutrons together in the nucleus. So by splitting, the binding energy is released as nuclear energy. Then from there, we have that this energy can be utilized to generate electrical energy or other forms, but this must be under controlled condition. For instance, the energy of atomic bomb is due to the nuclear fusion of uranium-235. Then we move to nuclear fusion. Now, this fusion occurs when nuclei of lighter element combine together to form a more heavier nuclide, and they combine where they are made to collide with at a very high velocity. The nuclei combine to form heavy nucleus. Now, this process is accompanied by a liberation of energy. So the fusing together of nuclei to form a heavier nucleus is called nuclear fusion. And remember, this is happening when the lighter nuclei collide with very high velocity. So this process requires high temperature, because now the reacting nuclei require energy. So this temperature is applying the energy so that they can combine upon collision. We have subatomic particles such as neutrons that are released during this reaction. And this, remember, in the nuclear fission we had the neutrons that we call the fission neutrons. So again, in the nuclear fusion, we still have neutrons that are being released, and also the energy released here can be used to generate electricity. So we have an example here. we have two isotopes of hydrogen that are combining. They are colliding at a very high velocity. When they collide, they fuse, they combine to form helium. And by so doing, they release a neutron and energy. So if you look at the mass number, it's 3 plus 2, you get 5. This will be 4 plus 1, you get 5. For the atomic number, we have 1 plus 1, you get 2. And for the products, we have 2 plus 0, you get 2. So our nuclear fusion reaction is balanced, and there is a release of energy. Now, the fusion is possible because the nuclei of the two atoms are small, and therefore there is less repulsion. That is why they are able to combine. The sum of mass numbers and atomic numbers of the products of the sum must be equal to the sum of mass numbers and atomic numbers of the reactants. So these are the reactants and these are the products. So in other words, we are emphasizing that the equation must be balanced. So the energy released during the nuclear fusion can also be converted into other forms of energy like electrical energy, and this must be done under controlled condition. For example, you have hydrogen bomb works in the principle of nuclear fusion. Then from there we have that nuclear fission and fusion are similar in these ways. One, in both cases, a large quantity of energy is released. Then number two, both processes results in chain reaction. Then number three, in both cases, subatomic particles such as neutron accompany the process, and then the energy released can be harnessed and converted into other forms of useful electrical energy. Then number five, the large amount of energy produced in both reactions can be destructive. For example, they can be misused in nuclear warfare. So it is important that we take care of that energy, we control, so that we can make use of that energy that is released. Then from there we have the assignment. So the assignment is just testing what we have just learned. So make sure that you revise, and if you see that you can't recall, it's always good that you go back, revisit, and then come and attempt the assignment. So thank you, and let us meet in our next lesson.